talk about ways that we can expand on this. Okay, we're back. Meeting's being recorded. Okay. Cool, great. Okay, we have seen that we can make some matrices. We've seen that we can transpose them, we fit them, do all sorts. We don't have this perfect data. We often have data that is heteroscedastic. We have data that has errors that are different. We trust more data points than certain data points more than others. We may have data that comes from different facilities. What are we going to do about this? All right, let's make some fake data that kind of looks like, I'm sorry that we can still see this. Let me disappear this. Okay, I made it worse. I've made some fake data here. The fake data is some polynomial again with some errors, some random noise, and I made one data point randomly, a significant outlier with significantly higher uncertainty in it. This is something that you may find happens in your data. What are we going to do about this? In this scenario that I've constructed for you, I know the errors, I know those are outliers, and I know the error on that outlier. You can touch on this again later, but this is not necessarily a common situation in astronomy data, that you truly know your uncertainties, and that you know which are the outliers, and you know what the uncertainty on that outlier is. But for now, let's take it at face value. Here's my fit to this data if I use what we've been doing so far. If I just fit this design matrix, it's going to be pulled down by that error, or by that uncertainty, or that uncertain data point. You can see that that's happened because all of the points are weighted equally, and that one really sticks out as being much lower than the others. Remember that all this is doing implicitly is finding where that cost function turns over. All this is doing is fitting to effectively the average of the data set. If we don't include uncertainties, this point is going to change our fit. We're going to have to weight it. And that makes sense. We should weight these squares all the time. This makes sense. I understand that I have uncertainties on my data points. I want to not throw that one away. It still has information content in it, but I want to weight it lower. I want to make sure that it isn't included in the fit the same way as the other ones. One of the common ways that we weight this is with the inverse variance, 1 over the uncertainty squared. We're going to put that back into our equation, our normal equation, and find a new cost function. We have our cost function. That's the original one was just the residual squared. Now we're going to weight it with our uncertainties. We can propagate this through the ordinary least squares equation. When we do, we're going to get this. Instead of having our design matrix, now we have our design matrix dotted with a diagonal matrix, which has 1 over the variance on it, 1 over the standard deviation squared plus diagonal. Now, instead of fitting the data, we're going to weight the data as well. We're going to weight the data by 1 over variance. Our new normal equation is the same equation. We're just now using our design matrix that has been weighted, and we're using our data that has been weighted. Go ahead.
Yeah, sorry, it's not a serious question, but what is this equation in your mean?
The best question. Is that the equation you'll mean? Oh yeah. So pretty close. It's pretty close. All right. This is weighted least squares. Before we had ordinary least squares, that's OLS. This is weighted least squares. If you squint, you probably recognize this as weighted least squares. Excellent. Let's use it in practice. Now, in order to find our best fitting weights, we're going to I'm sorry that it's cut this off. I'm so sorry. We've now fit the design matrix, dotted with the design matrix divided by our errors squared. And then we're going to fit the design matrix dotted with the data divided by the errors squared. That's the implementation of this weighted least squares equation. This is the implementation of Rubin.
So I think I missed this actually, but which error are you calculating? Is it one?
Okay. So what is the error? I have manufactured. Like, this is fake data, manufactured parameters. This is, I'm telling you that here's some data, here's the uncertainty for each of these data. I am treating this as Gaussian. Their uncertainty is the standard deviation, the Gaussian that this data point could be drawn from. But again, for now, it's okay, we have our new best fitting weights. When we run that equation, this is the fit we get. Great, it's been weighted. We knew that that data point shouldn't be included with the weights of the others. Now the green line goes through the rest of the data. We haven't put this out. We haven't masked it. We haven't said that you can't include this in the fit. We have weighted it. Before, we talked about masking. Masking is sometimes going to be a sledgehammer to crack a nut. Maybe the data is a little bit more uncertain, but we don't want to get rid of it. So this is something that you might use instead of masking. You can also implicitly downweight certain points extremely. They'll still always be included in the fit if you don't mask them out.
Since a design matrix is set up so that we can solve the coefficients, why does it also need to include the error propagation when we include it with the data to which we're solving?
There is a derivation to go from this down to the weighted least squares equation here, and I recommend that you look up the derivation to see that it gets to this point, rather than us like trying to go through this class. But the derivation is to take the gradient of this, you end up with this one. There is a sort of intuitive answer, but I think we'll get there, and then I think you'll see why. I'm not intuitive is a big word. Why it sort of makes story time sense. Any questions about weight of these squares? Sweet. All right. We're going to add more robust noise to the model. We're going to generalize these squares. First off, though, we have to talk just a little bit about covariance. Covariance. How do two variables vary together? They are covariant if they both go up or both go down at the same time. Covariance. Great. This is another thing where vibes. I get it. Interesting. Covariance, inverse covariance, dot product, vibes. Yep. This data, which I've randomly drawn, not very covariant. To calculate the covariance between them, I would just take this equation here. It's just if I take one and whiten it, I take the other and whiten it, and I make the sum, what number do I get? If it's very close to 0, they're not very covariant. Let's make a vector that is covariant. There we go. This looks covariant. When this one goes up, this one goes up. Okay, great. We calculate the covariance. It's now higher. Sweet. That's not close to 0 if it's covariant. The variance of a vector is the covariance of it with itself. We can think of this as a matrix. If we have our A, B, and C, we can make a covariance matrix. Covariance matrix has covariance of A with A with B, A with C, B with A, C with A. Said another way, the variance is right down the middle. Do you remember when we were doing least squares, weighted least squares, and we were putting errors through the diagonal? We were adding some error in, going down the diagonal and saying something about the variance of that data point. Sweet. That's the covariance of the data that we manufactured. Let's just take a beat, just look at what these covariance matrices could look like and what they mean. Covariance that looks like the identity means that all of the input vectors are uncorrelated. The variance of the vectors is all the same. It's one in this instance. The variance matrix that looks like this, vectors are uncorrelated. The variance in one is higher. The variance matrix that looks like this, same variance, but they are correlated with each other. Cool. You can weight the covariance matrix. We look at our data again. Oops. Yeah, I made some of the data points noisier, artificially again for make forfeit. Made some of them noisier. I said that some of them are more uncertain. If I calculate the covariance now, I get this covariance matrix, which has these giant numbers in it. If instead I calculate the covariance matrix and I include the weights, which are uncertainties, I now get more reasonable numbers for the covariance. All this to say, if we have uncertainties, we might include them effectively as weights. Keep it in mind that we just rarely know the covariance of our data in one second. you don't really know the covariance of our data. For example, if you're going to do a GP, you're going to get some functional form of the covariance matrix.
Notice in the last line, you're dividing over the area squared, area in X and Y the same. Is that why you did this? The area squared. The last formula you had the area of X times the area of Y, but now we just have the area squared.
I have to go back and pull that because it got cut off.
Yeah, here.
Yeah. In this instance, I think I had an error only in Y, and I had an error in X, it was the same X, but like across the whole thing. So yes. Cool. All right. That was a very quick dive into covariance matrices, just to refresh us and like get the vibe of like, what are they getting, what do they need, what shape are they, covariance. Great. Okay, we have now talked about two different kinds of least squares regression. We talked about ordinary least squares. Right? No uncertainties, no nothing. Make matrix, how does it fit? This is just fitting a line to data where we don't take into account our uncertainties. There's some data, here's me fitting our ordinary least squares to it. No uncertainties. Weighted least squares. Now we're going to include a diagonal matrix which adds some weight, which says that we have in the variance some are more variant than others. We should weight those more or less. Weighted least squares. There's our weighted least squares. In this instance, now this fits better than the ordinary least squares because we are correctly weighted these data points that have higher variance. Generalize least squares. Okay, we just talked about covariance matrices. Instead of just having the diagonal term, we could really have a full covariance matrix. We could say that we knew how uncertainties and data points were covariant with each other. The generalized version of this form is to say that we would include the inverse covariance matrix rather than just the inverse variance, which is just that diagonal. Here, for the purpose of this equation, or for the purpose of this slide, I've said, okay, I know there to be no correlation between the areas. I know that it is only the variance that I want to take into account. So I have made a diagonal matrix which has size, however many data points there are, by however many data points there are, it's a square. And the diagonal is the inverse variance. Then I can do X transpose dot inverse covariance dot X. That's generalized least squares. You'll see that here, this is functionally identical to what I did before in weighted least squares, where I said, okay, take the X and then divide it by this vector here. You can absolutely test this on the workbook part, but generalized least squares is taking weighted least squares and saying instead of it just having uncertainties on data points, now we have a full covariance matrix. Great. Okay, yes.
Just another question.
Yep.
Like from this resolution, it's hard to see how much trickier the different models are actually getting.
Okay, so this one is identical to the one before. There is weighted least squares. So the answers in these slides are identical. It's just that we've allowed for covariance in the generalized version. This is the ordinary least squares. There's not too much in it in this instance. But I think we showed a few slide decks ago with the green line that went through. There was like one data point that was really outlying. And that was where we showed that, oh, ordinary least squares would not be as good as weighted least squares in this instance.
But I'm just not curious if it's a ideal way to quantify that.
Oh, that would be goodness of fit.
Okay.
Yeah. Okay. Here. Any more questions before we move on? Generalized least squares is just weighted least squares, and now instead of just having variance, we're also including covariance. In this instance, there wasn't covariance. Right. Okay. When I was at grad school, I remember being in a meeting, and it was one of those like everybody's talking science meetings, and somebody we were reviewing a paper and we were ripping it apart. No, they haven't done this right. And somebody says, but we don't know anything about the mass of these planets. And somebody says, that's not true. We know they have mass. And I don't know why, but it has stuck with me so much. Prior information is super powerful. Like, we know they have mass, it's not 0. We know it's not 5 grams. We know it's not the mass of a supermassive black hole. We know they have mass. We do have prior information about planets and their mass, and we can fold that in. Up until now, we haven't been able to fold in prior information into this linear regression. It's just fitting a line to data. It is effectively, if we're just going to do a polynomial, numpy.polyfit. We want a way to be able to include priors. That's what makes it Bayesian. We want a way to be able to say, what are the bounds of the truth? If we're applying priors to our generalized least squares equation, we're treating this as Bayesian linear regression. This is going to include prior information on the weights. The prior has to be a simple Gaussian. The prior has to be specified as Gaussians with means and standard deviations. Excuse me.
Why is it be another distribution?
Because when you take your cost function and you try to take the gradient of it, it will not fall out to this equation. There are, of course, ways to do priors that are not Gaussian. It's just you won't be able to use this equation. Does that make sense? Another way to say this is if you were trying to do this, you're implicitly saying, in fact, throughout the whole thing, you're implicitly saying it's like Gaussian. You have everything is specified by some mean and some standard deviation. It's a great question. Okay. Now we have our Bayesian generalized least squares. We now include a matrix. It's got this subscript 0, and that's what I'm using to denote that this is our prior information. This information we have beforehand tells us something about our belief. And then we also have this theta 0, that's a vector. It's a vector of the prior mean belief we have. If you think that all of your weights are probably close to 0, give or take 1, theta 0 would be all zeros, and this matrix is going to describe the prior covariance, and you're going to have it be 1 over that variance you expect. So it's going to be 1 over 1 across all the diagonals. Okay, we might actually have genuine prior information in a lot of cases. You've seen us look at, for example, transit depth. We fit a box and we found some transit depth. You've seen us look at, for example, a sinusoid that goes through some star data. I might have priors on that. Let me know that stars don't vary more than 1,000%. I know that transit depths are probably, somewhere in the region of a percent. We might have a problem where we're trying to fit something like, let's say I'm trying to fit K2 systematics. I know the spacecraft moves on 6-hour timescales. What if I also want to look for periodicity from the star on 6-hour timescales? Maybe I'm going to make design matrices that look really similar, that both periodic at 6 hours. Maybe I want to weight them and say, well, I know systematics cause variability of about 3%, but I know my star has variability of order like 100%. It's a really variable star. We can include priors in order to break those degeneracies and sort of feed that into the model. Here's me using it just to show again that it still works, still fits a line through data. Here what I've done is I've said that I have some prior sigma and some prior mu. Mu here is what is the mean that I think all of these weights are probably close to, and sigma here is a standard deviation. If I had to draw a distribution that I thought each of these weights would be from, it would be specified by those two variables. Each of these have length, the same number of weights that we're trying to fit. If I have a design matrix that's 1,000 tall and 5 wide, I have to put in 5 priors. 5 means 5 standard deviations. As I said, this is a powerful way to break degeneracies in our model. If we have 2 vectors that look similar, we can add prior information to break the degeneracies. I can show you an example of this, but it's going to take us out of our talk slides. Before I do that, what questions do we have about this?
Okay, so we have two variables that are correlated in some way, like x, y, and we can couple that in the beta equations, right? Or no?
I think what you're saying is if I know that if I know that in the data two of my variables are very correlated, I can include that. Yes, you could. You would include it in the covariance.
For example, if I want to reduce the dimensionality of my matrix such that I figure out that two variables are correlated.
Yes.
Is that implicit in the state equation?
You could absolutely include that. So this matrix here, you could include that as like, yes, I understand that there's a prior covariance here that you might include. Largely when I do this in practice, because I don't know the covariance of variables with each other, I set this up as a diagonal matrix usually, but you could certainly not do that and have prior information where, yes, I know these two are correlated and that should be included in the fit. Yes, you could. Okay. I think I can show you me using this in anger if you want that. Does anyone have any thoughts about this adding invasion priors to this generalized least-squares approach to make it equation in your regression? Do you want me to show you using it in anger or shall we move on? Move on. Use case. Okay. give me less than 30 seconds.
What do you use it in what?
Oh, it's a British expression. It means do you want me to see me using it outside of this contrived situation? I think it was like okay. The nice thing about this is I have. Okay, hopefully we can read this. Okay, so this is a notebook from a package that I'm currently writing to abstract some of the linear algebra behind the screen and make it so that we can easily save and move these weights around for a project that I had in my group at Berkeley. So this is nice because now you're not going to see all of that Python, which is like A, T, prior, sigma, diag, 1 over inverse, whatever it is. Let's say I have this data, which is this K218 data again, and I want to fit this. Maybe I want to make a model that has something about column position, something about row position. This is me inside the framework of the package that I'm developing, making those vectors and then taking the cross terms off them. I'm also making a spline model. The spline model is a piecewise polynomial. These are pretty handy if you want to do models like this to create time series that has some enforced amount of smoothness on some time scale that you can specify. I'm saying that my model is just those vectors stacked with that piecewise spline to fit it, and I get something that looks like this. Okay, great. My model is the red line that goes through the data points. Residuals, okay. I can split the different pieces out. So I've got in red the systematic portion and blue the star portion. This is handy because actually in the project that I want to do, I do want to know something about the star as well as any parts around it. So it's handy to be able to separate them out. I can then take the stellar function and look at it at, if I've observed it at the same time with a different instrument, now I have some information about how the star is varying. If I go to around here, I know this is a little tricky to read, but what I'm trying to do here is I'm trying to make something that's a function of C, something that's a function of R, something that's a function of time, And then I'm trying to say, all of these things are only valid within certain bounds of time. What I've done up until this point is fit this spline model, which is also a function of time. It's wicked degenerate. I have something that's a function of time. That's my star. I have something that's a function of time, but it's my systematics. How am I going to tell the model, this is star, this is systematics? I can input priors and say, I know how the star varies. Priors here would maybe look like, this is what the weight should be for each piece of the piecewise polynomial, or this is the weight that I expect for the column portion of my systematic model. In order to make it not degenerate, what I've done is I first fit, and I've said, okay, there's no time dependence here other than the time dependence from the star. And that gives me a model that looks like this. We're going to come back to how I've managed to draw many samples from it. So that gives me this model. Then what I've done is I've said, okay, now I can update my priors. I fit the model. I did something with the systematics. I'm going to update my priors. I'm going to say that I think the weight for all of the pieces that make up this stellar model is this, give or take some error. So I specify mean, a standard deviation. And then when I create this model, I say, well, it's column, it's row, it's time. And then I add in some astronomy model with updated priors. Now when I fit, it's going to fit. And I can fit both at the same time. This is not the same as me saying, subtract some best fitting astrophysics model, then do systematics. I'm saying I have some prior information. This is what it should roughly look like. Fit it given that, but still give me any uncertainties on our final fit. And then when I fit that, I get much flatter errors, which is great. I will say I've masked out these fluffy errors down here. Those outliers are due to the fact that sometimes K2 would have a really big excursion, and there's nothing that correlates with it. Just like, whoops. And then when I subtract just the systematics here, I get this really smooth curve. I make no promises about how interpretable any of that was.
So what's the big question you're trying to answer with that?
The big question. Big question I'm trying to answer with that. So there's no one big question. The problem that I have to approach when I'm writing this is I'm going to be given a lot of different data in different wavelengths for a lot of different stars. And I need to give the scientists relying on the mission answers in a lot of different cases. The key variables that they want to know, what are they? Like, well, what's the period then? How do you the transit? Okay, you're giving it to me in the visible, what's it going to look like in the IR? There's lots of things like that question particularly. If I give you, this is what the star looks like in the visible, what's it going to look like in the IR? I don't know, but I have a prior guess. Like it might look something like this. So not only do I need to tell them this is my guess, but I need to tell them how certain I am of my guess. And there are plenty of instances where I'm fitting things that vary as a function of time, and like stars that kind of like this, and systematics that kind of like that. Fit them both, and we use some amount of trade-off and some amount of putting in priors when we can. Ooh, good. All right, why do we like these methods? The reason we're doing this OLS, weighted least squares, generalized least squares, Bayesian linear regression is because we're finding the maximum likelihood solution using simple linear algebra. We're just dotting matrices with each other, we're just taking transposes. That tends to be both very fast and pretty interpretable by its design. If you made a matrix, which is like, these are my regressors, these are the vectors, it's pretty interpretable because you made it. You can see that sometimes there are things that we can't make a linear model and we're going to have to do some exploration, some kind of grid search, like period. But inside that, our linear algebra tends to be pretty fast.
So in order to deal with finding maximum likelihood without sampling, we have to have parametric.
Wait, can you say your question louder?
Yeah, so if you have a parametric model, doesn't have and we don't need to use some sampling techniques, we can just like find maximum.
Yeah, I would say that, yes, I would say that's another way to say it. If you have a parametric model, in some instances, you're just not going to need a sample. You're just going to
Yeah.
dot some matrices, and then you're going to get your maximum model. That's exactly, but yes, this doesn't work if you have a non-parametric model, which is effectively a Gaussian process. Okay, we're going to build in assumptions in a few places. Choice of design matrix, we've already talked about this a lot. You are using your physics, astronomer, scientist intuition to build a design matrix. You're choosing priors. If you're going to do this Bayesian approach, you're going to choose priors. That is another place that your intuition or your previous data is going to come in. But ultimately, this kind of approach is fairly intuitive, interpretable, and you can make it Bayesian. Your model is effectively only as good as the design matrix that you're going to be able to build. We can make it fairly flexible and get uncertainties, but you won't be able to easily fold in the uncertainty of what if I made a bad design matrix. That's somewhere where Gaussian processes are going to excel. You don't have to build a design matrix, it's non-parametric. So it does naturally fold in the uncertainties of what if I made a bad model. You can think of Gaussian process at some level as this, but with an infinite design matrix to make it non-parametric. As I said, GPs are a place where you're going to have a very flexible model. You're going to have a model that does incorporate uncertainties because you haven't chosen, like, oh, I've made a decision with a design matrix that looks like this. But you may find that it's not as interpretable. You may find that it's not as fast because you're going to have to do a lot of sampling. You're going to have to sample over a lot of hyperparameters in some instances. You're also still going to have to make a decision. Anybody who's used a GP knows that you're going to have to choose a kernel. Your kernel is going to tell you what you think the function of the covariance matrix is. Even in GPs, you have to use your physics intuition to say, oh, it's a star, it rotates. I'm going to pick a simple harmonic oscillator kernel. Or, oh, it's a Poisson process, I'm going to pick some sort of kernel that looks like that. Or, oh, I don't know, correlations on some sort of scale, it's a Matern kernel. You're always going to have to make some decision in your model about what to build. Certainly, GPs are more flexible than this and don't require you to make quite the same amount of decisions. But there's a sort of some of the trade-offs. Linear regression, pretty interpretable, but it's parametric. GPs, less interpretable, not parametric. Linear regression is pretty nice. We're going to talk a little about model uncertainties and how we figure out those. Anybody have any questions? Sweet. All right. As we talked about in my, I have to give people answers at work. Sometimes I want to know how uncertain are you in the model? Like, Christina, okay, you think the star is this bright, but like, how sure are you? We're going to have to understand the uncertainties on the best fit weights. And maybe sometimes we want to draw from the range of models that are possible. We can totally do this. Let's create some random noise data. Third order polynomial. You're probably tired of me doing this. There it is. You might recognize this from earlier. We're going to fit the data. We do weights of least squares. You can see here that I am weighting by the inverse variance. And here I'm weighting by the inverse variance. I'm going to solve it. Okay, so this part of the equation, so you can see we've done like AT dot A and then AT dot Y. The first part, the design matrix transfers dotted with itself, optionally including covariance, optionally including priors, is the inverse variance of the data, or the best inverse, sorry, not the data, the inverse variance of the best fit weights. So in order to find the errors, all I have to do is invert that matrix and take the diagonal, because that's where the variance is. If I invert this matrix and it has off-diagonal terms, I could sample from the covariance matrix instead. So the individual error on each of these terms is in the diagonal part of the inverse. This should be to the power of 0.5. Here is that fake data. And this is the weight for each component, and then the uncertainty. You can see the uncertainty in the offset term is actually quite large. That sort of makes sense, because if I change these parts even a tiny amount, it's going to drastically change the offset. We can draw from the distribution. So we have these best fitting weights, and we then have the covariance matrix of the weights that we fit. We can just draw from that in order to get model flaws. So here what I've done is I've created samples from, cutting off again, created samples from the distribution. So I have best fitting weights, the mean, I have this mean of the weights. I also have the covariance matrix for the weights. I'm going to use the random submodule of NumPy, and I'm going to sample from a multivariate normal where I put in mean and covariance matrix. When I do that, I can draw lots and lots of samples from what are the potential W's that still fit with this model. And then I can just dot those into A in order to draw, in this case, 100 instances of what models, given the uncertainties, given whatever priors we put in, given whatever covariance matrices we put in, what models are compliant. Remember, when you get back these weights, they're not single values really, they are distributions. They have a mean, and when you do your OLS, GLS, WLS equation, you're getting back the mean, and then when you invert AT.A, you're getting back the inverse variance. I am going to shortly stop there, and we're going to do some live coding. I'll do it. I'm not going to make you do it. All right. That was a lot. It's not trainer. Cool. That was a lot. I hope this has shown how you can take this somewhat simple concept, make it more Bayesian, and really take into account the uncertainties that you already have on the data and get back the uncertainties on your best fit weights. This is what makes this a more powerful way to understand our time series. I've talked a lot. Unless anybody has any major questions, like, oh no, what's mine now? I think I'd like for us to, again, do our little 5-minute, 2-minute, 3-minute exercise where we just talk, and now that we know how to incorporate uncertainties, now that we know how to incorporate the covariance matrix, has your answer to this question, like what's good about this, what's bad about this, changed? Let's have 3 minutes of just let's repeat the conversation. How do we feel about this? 3 minutes, that was 8 minutes. What did we come up with as now our thoughts on Bayesian regression? Is this useful? Is this something you want to use to work? Is this, I feel like it had this feature in it? It's mostly on my notes if you don't use it. If you're like, nope, I don't see how this is going to be useful for me, that's okay. Unless you know your work. We're about to do a live coding portion where I'm going to go through doing this for test data. And you can yell at me and tell me what you want to see. No, absolutely. So all this to say, that will be another opportunity for you to see how and where this might be useful.
I guess my question is, I don't really understand this enough to really have an opinion on it. So, like, what is an alternative way to get at this problem?
Great. What are alternative ways to do this? The biggest one that you come across is probably GPs. Gaussian process is another great way to model time series like this. Like if I put this figure in front of you, I said, okay, how did I make all these different samples of the model? You might reasonably say, oh, she just fit a GP and she's drawn out of it. But as I said, there are trade-offs between these two approaches. Where you would use this is places where you have good priors and good intuition about what is in your data. Or places where you want to fit some sort of flexible nuisance. Gaussian processes are also a good answer. Anyone have any salty takes about Bayesian linear regression and whether it's useful or not? Because if not, I think we should take a break. So I think the break is now. We're going 8 total minutes early. I will stick around for those 8 whole minutes, and if you want to ask quieter questions, not in front of everybody, come up and ask a question. If you want to ask about Kepler data, test data, come and ask me. Other than that, I think we're meeting back at 4 for our final hour where I will code stuff for you and